Welcome back, everybody. All right, let me check the our calendar. I want to make sure everybody knows where we're at, what's going on. I want you to ask us some prizes. I did move some of the things that were due. Today is what? Today is can I meet somebody here? Today's the 9th. Okay, so I moved the homework Friday, chapter 4. I moved the activity for chapter 5 and the homework for chapter 5 till next Wednesday, because the plan is do chapter 4 today, probably need a little bit on Thursday, start 5 on Thursday, finish it up on Tuesday. Okay, and then finish up chapter 6, because the next exam is scheduled for the 23rd, and that will cover chapters 4 through 6. Okay, so anyway, I'm grading all this stuff, a lot of stuff I got to grade by hand. My hands are full, so I got most of your stuff done. I got to do the next one. A quick word with respect to numbers. Let me share something with you. Well, maybe not. Where'd it go? Okay. Okay. All right. Let me get the number up here. Let's arbitrarily pick some numbers out. Let's say, look, we can use that example, 303 or 606 versus 606.00. Okay. Now, this number, 606, obviously has 3 significant figures. Okay. And the number 606.00 has 5 significant figures. Now, that number had, both these numbers had the same value. Okay, imagine put a dollar sign in front of that, a dollar symbol. $606, you're going to get $606, right? Put it down at 606 cents, you're still going to get $606. So the value with respect to those two numbers is the same. Where they differ is the accuracy. Okay, there's the difference in the accuracy, because the 606 number, the uncertainty is the last 6 in the one place. So that number could have a range of plus or minus 1. So the true value could be 605, okay? Or it could be, 607. Notice that range. That's a range of 2 units. That's a pretty big range, right? Now, if we do the same scenario with the bottom number, our range could be, 50, I should have picked a 505 is plus or minus to the 100 place, 1 up negative 0.01 or positive 0.01. So that would be 0.99, right? Correct me if I'm wrong here, versus 606.01, okay? Because any measurement has a degree of uncertainty. There's nothing out there that's 100%, okay? Because everything that we create to measure, any tool that we create has a degree of uncertainty. And obviously we strive to get the uncertainty to be small, but it's right now as it stands, it's an impossibility, okay, with the tools that we have at hand. And so if we look at the range for the first number, though their same value is 606, okay, the difference is the range for the top number can go, the range is equal to 2 units, right? Where the range for the bottom number of where the true value is, okay, whatever that true value is, because we'll never know what that true value is. We're going to get an average of the true value by doing multiple measurements, but we'll never get 100%. There's nothing such as an exact measurement. There's always an error involved in that. So our range here is going to go from 0.02 units. So you can see the difference in the accuracy, okay? And so the numbers are the same with respect to value, 606 versus 606.00. They differ in that the accuracy. The first 606 is only accurate to the 1th place, plus or minus 1 there. Whereas the second number, 606.00, is accurate to the 100th place, plus or minus 0.01. Okay? So hopefully that kind of straightens it up a little bit as far as explaining the numbers. And being in science, yeah, sig figs will be a factor all the way to the last chapter. Okay, so even though we're not directly dealing with sig figs in any of your calculations, always keep that in mind. All right, so let's proceed with chapter 5. Any questions before I start? All right, so up to this point, we've learned that the model of the atom is in the center, we got the proton and the neutron. And I hope you guys had a chance to play with that simulation to give you an idea what the proton and neutron does and so forth, okay? There's also a question about isotopes. Now, technically, all 118 elements are all isotopes of each, whatever element it is. The most common, most abundant isotope is what we see on the periodic table with respect to the atomic weight, okay? And if we talk about the isotope of carbon, we talked about that. There's 4 isotopes: carbon 11, 12, 13, and 14. Okay, that is the mass number. That is the number of protons and neutrons, because the only difference between carbon 11 versus all the way to carbon 14 is the number of neutrons. Okay, the neutrons are the ones that create the difference in the element we're working with. We didn't change, the isotope does not change what that element is. We didn't change the proton. Remember, the proton defines what that element is. The moment you replace a proton, you have created a new element. But you can lose and gain neutrons and electrons all day long, and you don't change what that element is. Okay? It's still that whatever element you're dealing with. And so isotopes, basically think of them as you with more luggage. All right, so you're the isotope, right? So you're gonna go on a trip, you pick up one suitcase. Okay, you're still you, but you got more weight on you now because you got a suitcase. Or, you may pick up 2 suitcases. You pick up 2 suitcases, so your total weight increases because now you got 2 suitcases, or you got 3 suitcases. You're still who you are, but you change with respect to total weight. Okay, and that's what all isotopes are. Now, so we got that model: protons, neutrons in the center nucleus, and then electrons kind of floating around someplace. Okay, so we don't know quite better at this time where these crazy electrons are at until we start dealing with other scientists. And before I proceed, we talked about the size of the electron relative to the proton and neutron. The proton and the neutron were given a relative AMU of 1. They're big. We treated the AMU of an electron as 0, basically no mass, because it's so tiny relative to the proton and electron. But even though it has mass, what happens is these crazy electrons behave like light waves. And so we got to talk briefly about how light propagates and how it moves from point A to point B. Okay, so that's what this is all about. This talks about light exists as waves, and electrons do the same thing because the speed is so tiny. Now, with respect to waves, we got two things with respect to light waves, which are going to transfer over to electrons. One is this symbol here, which is called lambda, and I'll highlight it. Okay, right here. Okay, that is named it's lambda, the Greek symbol lambda, is the wavelength. And what that is a measurement from any 2 points in a hill, because we look at light as this wave here going with a hill and then a valley, a hill and then a valley. Okay, so if we pick a point on the hill, any place on the hill, where we go, and in this place we pick it right there. We pick it the same spot on the next hill. Okay, that distance is called the wavelength. Now it's going to vary depending on the light. It's going to be long wavelengths or short wavelengths. Okay. Now we could easily pick the spot right here, but we got to pick the same spot on the next wavelength. Guess what? That distance is also the same distance up front. So that is the wavelength. Now the frequency, and you're probably all familiar with frequency if your computer works at a certain frequency, 10, 20, or 2 gigahertz or whatever. You may have heard the term gigahertz, mega. Oh, well, in my case would have been megahertz, but gigahertz is now. Okay, that's pretty fast. That's like 1 billion things happening in 1 second. What a frequency is, how many things can happen in a given time unit, which is normally 1 second. Okay, so obviously a fast computer, like a 2 gigahertz, has 2 billion things happening, calculations, anything, and in the system, 2 billion things happening in 1 second. So that's pretty fast, not as fast as our brain, but still pretty fast. Keep in mind, when I started computers, I was in the megahertz, okay, way back. So frequency is the number of waves, in this case, how many waves can happen within 1 second. So the more waves can happen more in 1 second, obviously the frequency is different than another wavelength that maybe only get one wavelength happen in 1 second, okay? So we got the lambda, which is frequency, and then it looks like a letter V, but it's called mu, mu, for the frequency. All right, so we can see here 2 different wavelengths. So we pick 2 points on the hill, and we can see here in the top example, that wavelength relative to down at the bottom, very long wavelength. Wavelength relative to the one in the bottom. So this here relative to this here, you can see that distance is much shorter for the bottom point, okay? And also, we could say this is 1 second. Let me get a different arrow here. We can arbitrarily designate this time period as 1 second. And so within that 1 second, the top wavelength, maybe the top example has maybe 1 wavelength happens. Whereas the bottom, we're looking at maybe 2.5 wavelengths have occurred. So you can see how many wavelengths occurred within a given time unit at different frequencies. So the top example represents a low frequency light. Oh, low frequency light. So right there. So long wavelength, low frequency. Okay. Compared to the bottom example, where you have got a short wavelength and it has a high frequency. Now we're familiar with wavelengths because if maybe a lot of people don't listen to the radio anymore, turn on your radio in the car. Those are wavelengths. That's electromagnetic radiation also, but their wavelength is very, very large. Okay. And if you ever had X-rays done for any particular reason, that's also electromagnetic radiation, but those wavelengths are very small. And we know just by we know what happens on the X-ray. They're small, but they're strong enough to go right through you to give you that image. Okay, so you can do something here. The large wavelengths, like the radio frequencies, they're big and not very powerful. Okay, buildings can block them very readily, no problem. Whereas short wavelengths, okay, can or have a lot of energy with it can go right through you. We're familiar with that because of the X-rays. And even more powerful than those are called gamma rays, which we out in space, so we don't want to deal with those. Okay, so the result here, the whole thing is that low energy light has a long wavelength and a low frequency, whereas high energy light has short wavelength and high frequency. Okay. Now what we have is what is called, oh, okay, well, before I do that, we can look at a graph and you might see something like this and then ask you, okay, which one has a higher energy? Which one has lower energy? So by analysis, you can see, look at the lambda, look at the wavelength. You can see that B, its wavelength is much smaller than the A example, okay? And so B would have a higher energy, short wavelength, higher energy, okay? And with respect to lower frequency, that would be wavelength A. And so the top one could be something like the radio waves, which their wavelengths are in meters, by the way. Meters, that's, big, gigantic wavelength, whereas X-rays and gamma rays are down tiny, tiny, very small, okay? So what we have is what is called the electromagnetic spectrum. And on the left-hand side, we have gamma rays, very powerful, powerful energy, electromagnetic radiation. On the far right, we have the radio waves, not very powerful with respect to energy, but humongous with respect to wavelengths. We see in this this graph here is kind of misguided because that color there, the rainbow, that's really tiny. We can only, for the whole electromagnetic radiation spectrum, we can only see a small amount because that's our sensors and our eyes can pick that up. That's it. That's all the X or the electromagnetic radiation that we can pick up. We have what are called cones and rods in our eyes that pick up color and shades of gray. So you can see where X-rays are. Very, very powerful, but not as powerful as gamma rays. And then we got microwaves. They're just a little bit more powerful than radio waves. And then just below the visible, we got infrared, and above the visible, we got ultraviolet, which that can cause a lot of problems. Ultraviolet, without sunblock protection and long-term use, exposure to ultraviolet can cause all kinds of skin problems and so forth. So, because it has associated with energy. All right, so that's our electromagnetic radiation. Now, recall that we were talking about the 1900s in the last chapter, right? So another scientist comes into play here, Max Planck, very famous scientist. In fact, in Europe, there is a Max Planck Institute, a lot of big time research being done there. He introduced a very controversial idea at the time, okay? He introduced the idea that energy was emitted in small bundles that he called quanta. Okay? So he's talking about energy. We're not really getting into electrons at this time, but he says, okay, energy is emitted in small bundles called quanta. And for that, he said the energy as we know it is not continuous, okay? It is a specific amount. It is a specific wavelength, if you will, okay, which has associated with it a specific amount of energy. And he defined the individual light energy as a photon. Hence, go to Star Trek, photons, torpedoes. Okay, anybody Star Trek fans out there? Photon torpedoes, that's all it is, just energy, light energy. Light is pretty powerful, hence lasers. There's lasers out there with nothing but electromagnetic radiation that can cut steel. Very powerful thing. So his idea was that energy was quantized and they exist in specific energy levels. They were not continuous. So we can look at it as this diagram here. If we look at that image on the left, that would represent energy being all continuous, just a ramp. But he proposed the idea that it is more like a stair step, and that as we go from we have what we call the ground state, which would be the floor, that's your stable state, and then you move up to a next step was of a specific energy amount. And so all the energy levels are quantized and specific, okay, not continuous like the image on the left. Okay, so with that idea, Max Planck, he comes around, another scientist called Niels Bohr. So he's thinking, well, maybe electrons are in the same category, being so small, they behave like light. And so he proposed that electrons are quantized, that they, our model at the time, we weren't quite sure where these crazy electrons were situated. And so Bohr came in with a model to explain that electrons occupy a very distinct energy level, okay, which we're going to learn from the periodic table. See that far number on the left in blue? I got 1, 2, 3, 4, 5, 6, and 7. Those, when we get to the chapter periodic table, the horizontal level of the elements, those are called periods, which relate to the energy levels. So for the 118 elements that we have right now, we have 7 energy levels, starting with hydrogen, going across to helium, okay? And this is where we're going to start talking about where these electrons that these elements have, where they occupy, okay? What energy levels they occupy. So there's 7 energy levels, and we're also going to learn that within those energy levels, there are suborbits, sub-energy levels, okay? But we'll get to that here in a bit. So Bohr proposes the idea that they're basically kind of orbiting around the nucleus, but orbiting with specific energy levels, okay? Not just haphazardly just thrown in there. Each orbit has a specific radius and specific energy. With that information, what can you deduce about this? If I were to throw this at you right now and say, hey, which one do you think is bigger in size? Let me highlight one. Who do you think is bigger? Let me see, where is that? Is sodium bigger or cesium in diameter? Who do you think is bigger?
Cesium.
Cesium, exactly. That's the trend, because you can see energy at cesium, its outermost electron, it has, where's it at? Make sure we're clear here. Cesium has 55 electrons, okay? And it's going to fill in the first energy level with the X amount of electrons, then go to the second one, go to the third one, then the fourth one, then the fifth one, and then finally in the last energy level, think of them as the layers of an onion. We got 7 of them, okay? It's going to fill in the last of the electrons in the 6th energy level. So by rights, it's much bigger. So you can take any element as you go down the column, you can determine who's going to be bigger in radius just simply by its position on which period it's on. It's just bigger. And so the same is true for lithium and sodium. Now, here's another concept that we pull from the periodic table. Notice we talked about earlier the Roman numeral number on top, 1A, 2A, we'll go across and we'll shoot across to 3A, 4A, 5A, 6A, 7, and 8A, okay? That number, Roman numeral, represents the number of electrons in the outermost shell, what we call the valence shell, the outermost layer of that onion. So that's why they're in that group, because all these guys right here have 1 electron in the outermost shell. So lithium number 3 has a total of 3 electrons, because we got that from the atomic number. Of those 3 electrons, 1 of them is in the outermost shell. That implies there's two energy levels, right? Makes sense, right? Because it's in the second period. That means that those two get filled up in the energy level number one, and then the outermost layer, we got the last one to put in. That's 3. Sodium has 11 electrons. In its outermost shell, it's got 1 electron. Everybody. So what does that imply about everybody in group 2? That everybody in group 2 has 2 valence electrons in the outermost shell. Okay. And because of that, they react very similar. Because Mary, keep this in mind, all chemical reactions, it's all about the electrons happening. And it's all about the outermost shell. Okay. It's like when you cut an onion, I mean, you're going to cut it on the outside layer, right? You're not cutting it in the inside. So all the action happens on the outside. So everybody in that group 1, even hydrogen, all the way down to number 87, have 1 electron in the outermost shell. And because of that, they react very similar. Okay. Everybody in group 2, the same thing. They have 2 electrons on the outermost shell. Okay, so beryllium number 4 has 4 total electrons, 2 of them on the outermost shell, which is in the second energy level. Magnesium has 12 electrons. 2 of them are in energy level number 3. The other 2 in the next are inside. Okay, on the inside layers that are filled up. Okay, and that's going to tell us a lot of information about why metals tend to lose electrons and become positive, whereas non-metals tend to gain electrons. Let me see if you can deduce this. Okay, so let's look at fluorine, for example. In fact, everybody in group 7. Okay, everybody in group 7, based on what I just told you about group 1, how many valence electrons do you think everybody in group 7 has?
7.
Exactly, 7. Everybody in group 7 has 7. Remember the magic number 8, the octet rule. The electrons are always striving to get 8 electrons in the outermost shell. So how many electrons do you think these guys, everybody in group 7, need to get that octet?
1.
1. And if they pick up 1 electron, they have 1 more negative charge on them. So their net charge, what do you think their net charge would be if they pick, everybody there picks up 1 electron? -1, right? Take, for example, fluorine. How many electrons does fluorine have as an element?
9.
9, right? It's number 9. It's got 9 electrons, 9 protons. Okay. Now, of those 9 electrons, 7 of them are in the outermost shell, and it's striving to pick up 1 more to fulfill that octet rule. So now when it picks up 1 electron, now it has 10 negatives and 9 positives. What's the net?
Chlorine.
Net, huh?
Chlorine.
No, what is the charge? If I start off with net 9 positives, 9 negatives, what's my net? 0, right? 9 positives, 9 negatives, isn't that 0 total? Okay, now I got 9 positives, 10 negatives. How many negatives left over do I have? 1. So I got a -1. So everybody in group 7, when they pick up an electron, they get a -1 charge, because now they got that outermost shell full with 8. Okay. With that same analogy, not even going in detail here, but deducing, what do you think is happening for everybody in group 6? How many valence electrons does everybody in group 6 have? I gave you the answer. How many, everybody in group 6, how many valence electrons does it have?
6.
6, exactly. How many electrons do they need to get to that magic 8? I'm at 6. What do I need?
2 more.
2. 6 plus 2 is 8, right? I got to get to that magic 8. And that means because I'm at 6, -6 valence electrons, I need to pick up 2 more. What do you think my charge would be once I pick up 2 electrons? My net charge. Okay, look at it this way. Oxygen has 8 protons, 8 electrons. I pick up 2 electrons. Now I got 8 protons, 10 electrons. What's my net?
-2.
-2, exactly. Okay. It's like, look at it this way. I got $8, but I owe $10. I'm in the hole still -2, right? Okay, same thing. So everybody in that group 7 would have a -2 charge, all the non-metals. But we'll get back to that, okay, here in a second. All right. So that's why I point to the periodic table a lot, because knowing its position, its group number, I can get a lot of information about that element and the electrons and so forth. All right, so let's go back to here. And so all the electrons are in specific energy levels. Okay, so here shows 3 of them. So if you look at the periodic table, that would be period 3. Okay, so we start off, and even in that simulation that we did about the atom, build an atom, you notice they had the dotted lines that represent an energy level where the electrons exist. Now, there's some rules about how many electrons exist in the first energy, how many in the second, and how many in the third. But we'll get to that. Right now, grab a hold of the idea that the electrons occupy specific energy levels. Okay, even more so than that, these energy levels are analogous to their position on the period in the periodic table. Now, how do we know this happened? Well, there's such a thing as called line spectrum. You know, question is, well, how do we know on star whatever 10 billion light years away? How do you know what's up there? We analyze the light because elements produce specific what we call line spectrum. Okay. So if we take a fluorescent bulb, for example, or gas bulb, and we plug it in, we put energy. That's what's happening if you got fluorescent bulbs at home or anywhere you see that. You got the bulb, you got electricity running through that bulb. There's gas in that bulb. The electricity is energy. It excites the electrons of the gas molecules to go from the ground state back up to an excited state. Nature being nature, it doesn't like to hang out in the excited state very long, so it drops back down. So the energy that it absorbed has to be released, conservation of energy. And it releases it one of 2 ways, either as, well, both ways. It releases that energy it picked up as light and heat, okay? If you have an old-fashioned light bulb with the incandescent, it gets hot, right? It gives you light, but it's hot. It's because it's exciting the molecules in that wire, and it's exciting them to go into the next excited state. When they come back down, they give off light and they give off heat. The LEDs, similar, than that is hot, but they still give off light. So by doing this, we create what's called an emission light spectrum. Let me give you an example. So on the far left, you have this tube, fluorescent bulb, okay? But you fill it in with a variety of different elements. And then you hit it with electricity. And then you run it through a slit. All that slit does is just focuses the light. And then you run it through a prism. Now, you've seen this prism out in nature. During a rainy day, you see, what do you see out there? A rainbow, right? That's the light from the raindrops. The light, what happens is breaking up the light into the different wavelengths. What we see out here now is just white light. Okay, if we take that white light and run it through a prism, we break it up into specific energy light of different wavelengths. And this is what happens to hydrogen. Excite the hydrogen, run it through the prism, that breaks up the energy it gives off as light in the different wavelengths. To give us this picture down here in the bottom right, that is the fingerprint for hydrogen. Okay, And those different numbers, nm, the nanometers, that's the wavelengths that it gives off. We can take that information and we can do some calculations to figure out the energy levels and so forth, which is beyond the scope here, but this is how we do it. And so we can do this with a variety of different elements, and you get all these spectrums, emission lines. You got lithium, sodium, potassium, and so forth. Okay. Notice all the lines. Those have their own unique spectrum. And that's how we identify, metal like lithium and sodium, and gases like neon and so forth, and hydrogen. And this is attributed to, has been attributed to the electrons that are existing in specific energy levels and then getting excited. And then nature being nature, they can't hang out there very long. They have to drop back down. And they drop back down, they have to emit the energy they absorbed, they emit it either as heat or light. And it's basically what's happening here. You have an electron at a specific energy level. It gets excited either by heat or by electricity, and it kicks that electron up to the next energy level. And that's the middle diagram. Okay. Well, it's going to hang there for a second. So that fluorescent bulb that you're observing, you have one at home or somewhere in an office. If you were to slow time down a little bit, it would be like a what do you call it? It would be blinking on and off because the electrons get excited, then drop back down, give you a light. So it'd be like a little beacon, but it happens so fast that to our eyes and our perception, it's continuous. And so that electron that was excited drops back down, and that arrow that you see there, kind of wiggly arrow, that represents the energy that it absorbed, but in the form of light. Okay. All right. So with that information, we can do calculations, back calculate, and come up with different orbits. We have determined, or at least the model shows, and like any model, it can change tomorrow, but the current model shows that we have 7 energy levels, okay, which is consistent with the 7 periods of the periodic table. Now, within these levels, we have what are called sublevels or sub-energy levels, or another term that is used are called orbits. And those orbits have been given letters. And right now there's only designated 4 of them. One is the S, the P, the D, and the F. Why they were designated these letters? The S makes sense. It's because they have a particular shape. It's round. The P's, kind of doesn't make sense, but they've been given the letter S and then D and F. Okay. Eventually, if the model is still holding and we discover more elements, we're going to have more energy levels. But at this point, we're at the S, P, D, and F. Okay. Now, there are limits within the orbits. So everybody in the first energy level, there's only one sub-level, and that's period 1. So I wish I had the periodic table here. I can show simultaneously, but you may have it here, may have it there with you. So if you label those periods like I did on the periodic table, let me show you what I did here, because our periodic table doesn't have it. Starting with hydrogen, you label it 1 through 7, and let me highlight that right here. Okay. And so 1 represents simply hydrogen and helium. Okay. The second energy level, you go across to lithium, all the way across to neon. Okay, lithium. Okay, let me change the color and give you the gist. In the second energy level, we start with sodium, magnesium, and Okay, so the third energy level, starting there, we go across. Okay. And that continues the fourth energy level, and the fifth, and the sixth, and the seventh. But right now, we'll stop at the third. So in the first energy level, there's only one sub-level, or what we call orbit. I'm going to use the term orbit rather than sub-level to distinguish the two. We're going to have one energy level and then orbits. So there's only the S, and it's only the hydrogen and the helium as I showed you going across the periodic table. The second energy level has two sub-levels or orbits. They also contain the S, but now we have what are called the P. Okay. And then the third has also the S. So you can see here a trend. Everybody has the S, starting with 1 through 7. Everybody has the S orbit or sublevel. But starting in the second energy level, then the P comes into play. Okay. When we get to the third energy level, we introduce a new orbit, which is the D. And in the fourth energy level, we introduce the fourth energy level orbit, which is the F. Okay, the F. So that gives us up to the fourth energy level. Now, I won't introduce it now. I'm just going to get you to grasp the orbits, and then because when we talk about the D and the F, it gets a little bit confusing, but I want to unconfuse you, hopefully. All right, so this represents the different orbits, different energy levels. Now it's kind of misleading because it looks like we're looking at our solar system, right, with the different orbits of the planet. Well, what really, and that's true for the S. What these orbits represent are mathematical equations. They're big, crazy looking mathematical equations, way beyond the scope that we get into what's called quantum mechanics. But if you take these equations, you can't, as any equation, and you plot them on your computer, you can plot arbitrary data into it, points, and you get an image. We're going to find that these orbits have a specific shape based on the mathematical equation that represents the S orbits and plotting its data. And the same is true for the P, the D, and the F orbits. They're nothing more than mathematical equations that have had data plotted on them, and they represent the probability of the electron being somewhere in a three-dimensional space. Okay. All right, so like I stated, that I utilize the term orbits rather than sublevels. These orbits are regions where there's a probability of finding an electron. Okay, they're mathematical equations. Now, the downfall in this is a side note because we talk about probability on one hand, and then the other hand, we talk about specific energy. Well, we got two different things here. Specific energy and probability is like gambling. You have a probability of losing and not losing. It's a chance. But they've meshed the two ideas to help us come up with a model to explain how the electrons are put together. All right, so this is what we know. This is how what's been shown. The S orbits, okay, all S orbits, and remember, they're starting at level 1 all the way to 7. They all got an S orbit. The only difference is on the S orbit would be, maybe this size of a golf ball. The 2 orbit, maybe that's the size of a softball. Because remember, as you go down the periodic table, the diameter increases. Okay, so even though they're the shape of a sphere, which you're going to see here, the 1s is smaller than the 2s, and smaller than the 3s, et cetera, et cetera. Okay, So all s orbitals, the maximum number of electrons that occupy the s orbits is 2. Okay. There's only one s orbit. Now the p's, we're going to learn there's 3 s orbits. Excuse me, 3 p orbits, and each one can handle 2 electrons. So therefore, the p's have a maximum of 6 electrons we can put in p orbits because there's 3 of them and there's 2 electrons per p orbit. The 5 orbits, there are 5 of them. The d, excuse me. The d orbits are 5 in the same idea that 5, there's 5 of them and each one can handle 2. Therefore, the maximum the d orbits can handle are 10 electrons. Once the max is reached, when we start filling these electrons, they got to move up to the next one, to the next orbit. Okay. And the F, there are 7. And the maximum number of electrons you can put in the F orbits is 14. Now, the periodic table gives you lots of hints to remember this. And let me go to the one periodic table here. All right, this periodic table, what I did is I marked the first 2 columns and I put up there S elements, the letter S. And then next one in, I put in D elements, starting with the 3B, BB as in Baker, going across to 2B. And so let me highlight these so you can see what I'm talking about. So the S represent these guys right here. Let me change the color. The D are right here. And the P are right here. And let me get a different color. Let me try green. And the F elements. All right. Now, when I look at group 1A and 2A, I think of what I call them the S element. There are 2 columns in the S elements, 2 columns. Okay, we just said the S orbital can only handle 2 electrons, right? All right. Now, the P, we're starting with column 3A. Count the number of columns from boron all the way across to neon. How many columns do you have? The ones I've highlighted in yellow. How many columns do you have?
There's 6.
6, exactly. Earlier I said the P's, there's 3 of them, and each one can only handle 2. So at the maximum number of electrons in the P orbits is 6. So we got starting with boron. Guess what? P1, P2 across P3, P4, P5, P6 all the way to neon. If I was doing lithium, it would be S1, S2 for beryllium, 3 and 4. Now look at the D elements. How many columns do you see with the D elements? There should be 10, starting with number 21, going across the zinc, number 30. There's 10 columns, right? Now, the D orbits, there's 5 of them. And 2 electrons per D. It's total of 10. Guess what? 10 columns. So I go D1, D2, D3, all the way across. When I say D1, D2, you'll see here I talk about superscript. That's how many of those electrons as I go across. D1 with number 21, and to zinc all the way across to D10. Now the ones I labeled F, it's those down here at the bottom. Guess how many columns you find there? 14. So you'll be F1 all the way across to F14. Those represents, that's where we start dealing with the F orbits. Now we're not going to deal a lot with the F orbits. I just want you to be aware how many electrons. We're going to be doing what I call electron configurations. That means taking an element and then writing how their electrons are put together. What's their configuration for the electrons that they have. And we'll probably do maybe up to 21, 22, that's about it. as far as the configurations. Okay. So we'll come back to that. All right. Now, I wish this, I need to flip this box upside down because this is the way you really are filling them up. You start with the lowest level, and then, you don't start adding your electrons at the highest level. So if you can imagine this picture flip upside down, it's an upside down pyramid. Okay. So your very first level, level 1, is simply all you got is an orbital. I can only put 2 electrons total in there. So if I put 1 electron, guess what? That represents hydrogen. If I put 2 electrons, that represents helium going across the periodic table. Each box represents an orbit. And so I could, when I fill this up, my first one, I put an arrow down that represents 1 electron, 1s. Okay, that's hydrogen. When I go across to helium, I put another electron in that box, and I put it in a different direction because the electrons in the orbits travel in different directions. And so now that represents helium. Yeah, 1s2. Okay, and what I mean, the first one, I don't have 1s, I don't have superscript. So if that was hydrogen, and then I would write 1s1, superscript 1, okay, with 1 arrow that I had previously. And as I go across the periodic table to helium, helium's got two electrons, right? And so I would represent its electron configuration as 1s superscript 2, and that would represent helium. Okay, now element number 2. So I come across to lithium, element number 3. Okay, so let me get my arrow back. So I'm filling up the electrons. Notice I'm dealing with lithium. Does not lithium have 3 electrons? Right? From the periodic table, it's atomic number 3, right? Remember I said it's in group 1? I said everybody in group 1 has its outermost shell has 1 electron. Guess what? Group in level 2, that 1 valence electron is in level 2. Okay. The other 2 electrons are in the next energy level. So this will represent lithium. Okay. Straight across to beryllium, number 4. I will put one more arrow in there. I'm going to put it in a different direction, just to make sure that they're in different, orbiting in different directions. How many electrons do we see here? Remember, every arrow represents an electron. How many electrons do we have total? 4, right? Who's number 4? Beryllium, number Be. Okay, remember I said everybody in group 2 has 2 valence electrons? Well, there you go. 2 valence electrons from beryllium. Now shoot across to number boron. Okay, boron has 5 electrons. As I go across that periodic table, that's where the P's start. So now I can only put 1 electron. So element number 5, which is boron, has 5 electrons. Okay, those 5 electrons, 2 of them are in group level 1 in the 1s2. Okay, and so this one here is full, but this would be, because let me write this in here. This would be 2s superscript 2, because that first one's full. And then here, I will start the P. So then I will write 2p superscript 1. Okay, that 2 in front of that letter represents the energy level, which is the period that is. Okay, and so just going across the periodic table, using the periodic table, I can help myself to fill in the electron configuration, because now I'm in number, what was it, number 4. 5. Now I got carbon. Carbon's number 6. Okay, I fill up another orbital here. Okay, and so now I can write this as 2, superscript 2. So carbon has a total of 6 electrons. Okay, it is in group 4. Guess what? It's got 4 valence electrons. Of those 4, 2 of them are in the 2s2 orbit, and 2 of them are in the 2p orbit. Okay, and I have a total of 6 electrons. Right? Do I not have 6 arrows here that represents the 6 electrons? And so I just keep going across the table. If I fill everybody up, and I fill each orbit first in one direction like I'm doing now, but as I go across the periodic table, you know, because the p orbits there's 3 of them, each one can handle 2. I can start filling in the other arrows in the other direction. Okay, now I end up with this electron configuration. Oh. Can somebody tell me, based on the trend we've been doing, can somebody tell me which element we're talking about here that has this electron configuration? Okay. To help you out, how many total electrons do you see here? How many arrows do you see total?
10?
6.
10. Yeah. Which element is which element?
Is it
Neon.
neon?
Neon, exactly. And neon, what group is neon in? What's that Roman numeral of where neon's at? Number 10. What does it say?
Group B.
No, it'd be the A. Go find neon in the periodic table, number 10, go all the way up to the Roman numeral. What's it say? 8. 8A. 8 represents 8 electrons on the outermost shell. The magic number is fulfilled. Okay. That means that, you know, everybody in the last column, column number 8, are called noble gases because on the outermost shell, that magic 8 has been fulfilled. If I go to number 11, who's number 11? Sodium, right? I have to put the where's my, if I go to number 11, the next electron is in this 11 electrons. I got to go to the next level. Look at the periodic table. Where's sodium? What period is it in? Guess what? 3. Okay, it's got 3 electrons. What group is sodium in? What's the group number? Is there Roman numeral on top?
First one.
1. Remember that 1 represents how many valence electrons, how many in the outermost shell? Look at the way my drawing is. Do I only have 1 electron in the outermost shell? I do, just one little arrow. So that's consistent with the periodic table. Okay. And that's what we do here when we start using electron configuration. We're just filling, we start at the bottom, level 1, we start filling up the electrons in their particular orbit. Now, if I were to do the electron configuration here, this will be 3s, because it's in the 3rd period, and then just Roman superscript 1. Okay. And so the electron configuration for sodium would be 1s2, 2s2, 2p6, 3s1. I should have a total of 11 electrons there in the superscript. Now, I know right now it's clear as mud, but we'll get more examples where I'm going to divert you to the periodic table, because we have a way that you can fill up the electrons using their number sequence, and you can memorize that if you want, or you can just look at the periodic table and determine where it's at and right away write it out, okay? Without having to memorize that sequence that I'll give you here in a bit. All right, so with that, let me clear my arrow. Okay, so I said earlier that these S, T, D, and F orbits are mathematical equations that you can take and plot them. And what happens when you plot them, because remember, these are three-dimensional models, X, Y, and Z, you get a shape that looks like that, a round circular shape. It just basically says there's a probability, obviously the darker area, there's a higher probability of an electron being in that area than say out further out where the probability diminishes, okay? So that's the shape of the orbit, the S orbit, a round shape. Now, with respect to the P, when you plot those, you got three orbits. They have what we call them dumbbell shapes, you know, the weightlifting dumbbells. There's three of them, okay, in the X, Y, and the Z direction. And remember that you can put two in each one of these orbits, so you have a total of 6 total electrons for all the P orbits. The S, you can only put 2 maximum. Any orbit can only put 2. So all the S orbits, the maximum you can put is 2 electrons. Okay. We're not going to worry too much about the D's. I try to get the thing to work. It's a link, but the D's has some crazy looking shapes. We're not going to be too concerned about it. They look like kind of like space stations out there, futuristic space stations. But just take away from all this, the S is circular, round in shape. We got 3 P dumbbell shaped looking orbits, okay, for the P, and the D's and the S are extremely complicated, way beyond the scope here. Now, earlier, like I said, this is the manner of which the order in which you're going to start filling up electrons. The coefficient, and this the 1s, 2s, 2p, the coefficient, the number up front, that represents the energy level, which is the same as the period on the periodic table, okay? The lowercase letter is the orbit. And then what we do is we put in a superscript on the orbit to represent how many electrons are in that orbit. Keeping in mind that the maximum for the S is 2, the maximum for the P is 6, the maximum for D is 10, and the F is 14, okay? So be able to do at least the first 20 configurations, which brings you up to, where are we at? Calcium, okay? And again, you can use a sequence, or you simply use the periodic table like I was showing you how to do that. So we did carbon, okay? Okay, so carbon, its electron configuration, obviously, the first level is full, and that is 1s2, and then the next level is 2s2, and then 2p2. Much like the diagram I did earlier. Remember, I showed you the where I stopped at carbon. We're now filling in the boxes. Okay, so we can use a periodic table to do the same thing. All right, so they ask you to look at carbon. So what we do is first identify where carbon's at. All right, and so carbon's right here. Okay, and then the next thing to do is recognize, identify its period, and it is in period 2. Okay, so identify the element. I got 6 electrons to work with. Okay, identify the period, which means that the first period is full. Okay, because it's already, it's like you fill the electrons. That means period 1 is full, and then period 2. Now the third thing to recognize is this: it is part of the P elements. So if you look at group 3A, you can think P1 and go across. Remember I said there's 6 columns. P1, and when I say P1, I say superscript 1, P2 for carbon, P3, P4, et cetera. And we have crossed the s electrons based on this position. So with that information, I can start writing the electron configuration because I know the 1s2 is full because that's the first layer. And that's full. And then I come across, and that fills up the hydrogen and the helium. Then I go back to group 2, level 2, where's lithium and beryllium. That's full as I go across the periodic table. So that's 2s superscript 2. Okay, so that's full. And then I go across to carbon, and it is in P2 column. Okay, remember the P1 starts off in group 4, group 3, and then all the way across. So that would be, because I'm still in the second energy level, is 2p superscript 2. Okay. So that caret is the superscript. And so count the superscripts. I should have 6 up there. That represents 6 electrons. Okay. I got carbon 6 electrons. Now, if I needed to do nitrogen, guess what? You don't have to do anything particular. Why? Because I'm going to identify nitrogen, which is right next door, next one over, right? So it's going to have 7 electrons. So I go back to my electron configuration, and I go, and it's in P3 and the third period. So there's the electron configuration for nitrogen. See that? What about oxygen? What do I do now? Okay, let's go nitrogen. Let's go to nitrogen, oxygen, right? The next one over. Okay, it has 8 electrons. So now I just select my, and it's in P4 column. Remember, starting with boron, that whole column, P1, P2, P3, P4, etc. And so now this becomes P4. Now oxygen has 8 electrons. Look at my superscripts, do I? Excuse me, yeah, 8. So I have 8 electrons in my superscript. Okay. Nothing complicated now, right? Now, let's keep going across the periodic table. Get rid of, highlight little fluorine, which is right there. Okay, 9 electrons. It's in column P, what? P5, right? And so now I just replace my P4 here and change that to 5. And I continue, and now eventually I get to neon, which is the one next door. Okay, so that becomes P6 for neon. Right there. Okay. Now I'm asked to go to, let's go sodium. Well, sodium, guess what? Sodium's right here. 11. It's in the third period.
3b.
Exactly. 3. What would it be? Three. What is the S element? I'm back to the S elements. Remember, S1, S2. So that would be 3.
1.
S1. Exactly. There you go. All right. And if I go to its neighbor, magnesium, guess what? 3s2. Okay. You see how you're using the periodic table to go across, which is consistent with with the sequence they give you there. I don't want to lose everything. I probably will lose everything here, but it's okay. If I go back to that's all I'm doing. I'm going across. That's the sequence. I didn't, the 1s, 2s, 3s, et cetera, okay? That's the sequence. Now, the confusing part that happens here is, let me highlight it. And let me put it in a different color, is the 3D. Notice how we go 4s, and then all of a sudden, the 3D arise. Well, here's the reason behind that. You don't have to worry about the D's until you actually get in here someplace. If you get to number 20, oh, let me erase that. Not until we get to 21 that we got to worry about the 3Ds. Okay. Now what happens is this. Number 21 is in period 4, and it starts introducing the D elements. Remember, I was talking. So I got D1, and if I go across the zinc, I go all the way across to D10. Okay. Now, because of the mathematics of the equations, the orbits, the D orbits do not, you would think it to be 4D, okay? Because it's in the 4 period. But because of mathematics, and only when you start to 21, the energy level of the D orbits for 21 actually go in the 3rd energy level, okay? Because when you hit number 21, you think, okay, we got 4D, because prior to that, you got 4s1, 4s2, and then you hit number 21. Okay, now you think, okay, I'm in the D elements now. I got 10 columns to go across. But think to remember, when you get to the D elements, you find the period that is in and just subtract 1. So it's 3D. And that is why you see that sequence where you get 3D. But if you don't hit 21 and you only stop at 20, then you don't have to worry about 3D. Not until you get to that element. And the same is true for the F's. The F's start right here. And you can see that the F's start in the 6th period. Okay. But their energy level actually starts with the 4F. Okay. So and for the D, you subtract 1 from the period it's in, and for the F, you subtract 2 from the period that it's in. Okay. And it's only because of the mathematics involved with respect to the energy orbitals. And that's really the only, we're not going to be doing any configurations for the F here. We're more than happy to talk you through it if you're interested. And, if we do a D or something, it might be, something in the 20s. Uh-oh, I got my assistant here telling me the time. All right, so let's stop it here. Chapter 5. And this would be slide number 24. Make sure I got it. All right, so any questions? Uh-oh. Any questions? Uh-oh, somebody's yelling at me. My assistant, she's over, she just woke up. So she's like, come on, Dad, gotta do something here. All right. Oh, if you look where, thinking about my background, that's the size of Earth in one of the tornadoes or whatever on Jupiter. That's how big that planet is, just to give you an idea. That's a stone front. Anyway,
Dr. Fred,
yeah, go ahead.
I had one that asked, acetone and salt, mixing those two together.
Yeah, I'm sorry you broke up. You were going to mix something together?
Mixing